Okay, good morning, everyone. This is the study that we did for the DOE project. The title of this study is Multi-Objective Equal Routing Development for ICEVs, BEVs, and HEVs. Yusuf, Mohammed, and Hisham Naka also work together for this project. ICEVs gasoline vehicles, and BEVs electric vehicles, and HEVs hybrid vehicles for this case. So what is eco routing? Eco routing is a technique that finds the most energy efficient route. So most of people use we call travel time routing. They decide their route based on their travel time and their total distance, based on their urgency, experience, and current information. So eco-routing can improve vehicle energy efficiency and reduce vehicle emissions by determining the most energy and eco-friendly route. So why eco-routing is important? Especially for BEVs. BEVs has their limitations, something like a battery size and then their driving ranges, particularly when charging stations are not available. So there's a different energy consumption patterns for BEVs and ICEVs. Fuel consumption patterns of ICE BEVs are significantly different regarding their driving cycle. BEVs are more energy efficient on low-speed arterial load compared to highway trips. For example, for ICEVs, there's something called driving cycles. Freeway G cycle and local cycle. Those were developed by EPA. And then, in case of ICVs, energy consumptions, fuel consumptions are almost identical for this freeway G cycle and local cycle. But in case of BEVs, it is a huge difference for these two cycles. The main reason for the difference is because of the regenerative braking of BEVs. So because of these different energy consumption patterns of ICE, BEV, and HEVs, we need to develop different energy eco-routing strategies. The objective is to develop and test energy efficient routing strategies for ICEVs, BEVs, and HEVs that minimize their energy fuel consumption while at the same time do not increase vehicle travel time. Eco-routing logics. We use something called Eco-SFA. It is the Eco Self-Population Feedback Assignment. We use the stochastic incremental feedback user equilibrium traffic assignment technique. So in this algorithm, vehicle routing is selected based on fuel and energy consumption experience of other vehicles in the same vehicle class. Same vehicle class means ICVs, because their energy consumption patterns are different. So ICVs get the information from the ICVs only. BEVs get the information from other BEVs. So also, all vehicles within specific class, they are divided into 5 subpopulations, each comprising 20% of all vehicles in the same vehicle class. The travel times update every minute, while energy fuel consumptions update every time when a vehicle leaves a link. Routing of each of these subpopulations updated every 3 seconds during the simulation based on the latest real-time measurement of the link travel time and fuel energy consumption levels for specific class. Information update of each vehicle subpopulations was staggered in time to avoid situations in which all vehicles select identical paths. It's a little bit complicated, but it's like let's say this. ICVs, they are divided in 5 subpopulations. The reason we divided that 5 subpopulations is if all ICEVs, they get the same information at the same time. And let's say route 1 is empty and route 2 is very crowded. Then all ICEVs, they try to use route 1 at the same time. Then it will be very crowded. So we divided 5 subpopulations. They get the information different time. In that case, we can like distribute congestion or network. And these are the zero energy consumption models that we use. For ICBs, we use a big something called VPCPF model. It is second by second microscopic data consumption model. Because it is power-based model, so power is greater than 0, then we use power and power scale as an input variable. And the power is less than 0, we use the constant value. So BEV energy consumption model, this is also second by second like a instantaneous model. And we use the power as well. So the power is greater than 0, we use the power, and then also you can see at the D, at the M, at the B, there are like drive line efficiency and electric vehicle motor efficiency and battery efficiency. And we also introduced the P-ops, which is ops power used by the vehicles. We use like 200 to 600 watt per second. When vehicle power is less than 0, we introduce regenerative braking efficiency, which is a function of acceleration. For HEV model, if power is less than 0 or the speed is less than certain speed and the power is less than certain power, then the HEV use the EV mode. That means HEV don't use any fuel consumption. And the other cases, the HEV fuel consumption model is based on the function of speed and power scale. This is the test network. We use the Los Angeles downtown area, which covers I-5, I-10, I-710, I-110, and Route 101. It is huge network. It is total 3,500 links, and then demand was over 143,000 vehicles per hour. So we developed a network using integration. So total node was 1,624 nodes and 3,556 links and 457 traffic signals, and then about 82,000 OD pairs. Excuse me? So this is the eco routing result for BEVs. As you see, this blue bar is TT routing, travel time routing, and this orange is eco routing result. On left side of the figure, as you see, energy consumption was reduced about 20% for each case, which is no congestion, mild congestion, and heavy congestion cases. But even though we save 20% of the energy consumption, on left side, the travel time, this increase is 100% and more. So I don't think, we don't think nobody will gonna use this eco routing if the travel times increase more than 200%. That's why we developed multi-object eco routing. And we use the link cost function to develop this multi-object eco routing, which is function of the travel time information and energy and fuel consumption information, and then cost function, and we also introduce the value of time. So because select next link based on the link cost instead of using their travel time or fuel consumption data, and vehicle only use the link of the same vehicle, same class vehicle information to update the link cost estimate on the link. That means BEVs get the information from other BEVs information only, and then ICEVs get the information from ICEVs, and then HEVs use HEV information only. And for this specific case, we use $10 per hour for valuable time, and $1.90 gallon of fuel. And for electricity, we use about 13 cents for kilowatt hour. We tested the impact of MO routing using integration software. We used travel time routing as a base case, and we use three different congestion levels, which is 25%, 50%, and 100% different demand levels, which represent no congestion, mild congestion, and heavy congestion conditions. And we also use the 9 different market penetrations, which is like a MO routing percentage, which is 1, 2, 5, 10, 15, 20, 25, 50, 75, and 100% market penetration. So 100% market penetration is all vehicles use MO routing. And each simulation scenario was repeated 10 times to represent average traffic conditions. This is the simulation result of ICEVs. That means we use only ICEVs in the area network. As you see, as market penetration goes up, actual saving was increased. Then in this case, we can save over 13% fuel consumption when 100% of MO routing was used. But when you see, this is the line of the heavy congestion curve. For no congestion and mild congestion, we didn't see like a lot of benefit. So travel times are very similar to the fuel consumption. So we could save like 22% of travel time when you use MO routing with 100% market penetration. This is case of BEVs. It is very different from the ICEV cases. So we could save like up to 22% of energy saving for BEVs when vehicles use MO routing. And in this case, we can save energy consumption for all congestion levels, so no congestion, mild congestion, and heavy congestion cases. But when you see the left side travel time is increased up to like 55% based on the market. So this is the case of HEVs. When you see this like a maximum fuel consumption case is about 2.2%. So we don't see lots of energy saving and then lots of energy saving for this HEV cases. But travel time, if you use this MO routing, you could save about 70% of travel time saving for 100% market penetration cases during heavy congestion conditions. So we assigned different vehicle compositions in the network. So in this case, we tested with 25% ICEV, which use TT travel time routing, and 25% ICEVs using MO routing, 25% of BEV using TT routing, and 25% BEV using MO routing. We compared with this 25% of equal routing, 25% BEV equal routing. We tested on area network with heavy congestion conditions. So when we compare with a combination of TT and MO routing and then TT and equal routing, as you see, energy consumption is almost identical for both cases. But when you compare with travel time, like a combination of TT and MO routing save about 20% or more of travel time for this BEV cases. And we tested this multi-objective equal routing using more realistic vehicle compositions. So we tested two vehicle compositions. One is the current vehicle composition of California, and then second one is the future vehicle composition of the California. The first current vehicle composition was based on 2019 vehicle sales data in California. which include 87% of ICEVs and 7.7% of BEVs and 5.5% of HEVs. And for future vehicle compositions, we use 50% ICEVs, 30% BEVs, and 20% of HEVs. So this is the result of current California vehicle composition. So for heavy congestion conditions, we could save about 10% of the fuel consumption with 100% market penetration. But in case of BEVs, if market penetration is greater than 10%, we could save about 25% of the energy consumption of BEVs. For travel time, it's very similar to the fuel consumption. As market penetration goes up, we could save about more travel time. At 100% market penetration, we could save about 70% of travel time. And at 100% of the market penetration, we could save about 36% of total delay. This is the future vehicle composition. As you see, pattern is very similar with the current vehicle composition, but it is, as you see, it is definitely different. So that means if you use different vehicle composition, then the result can be different. In this future vehicle composition, we could save about 9% of fuel consumption, and we don't see lots of benefits for no congestion and mild congestion cases. For BEV energy saving, we could save about 25% if the market penetration is greater than 50% or more. Travel time case, we could save about 10% travel time when roadway is very congested, and the delay is like we could save about 30% of total delay during heavy congestion case. So this is conclusion of our study. Single objective equal routing study to reduce fuel consumption, but also increase their average travel time. For BEV case, we could save about 20% of energy saving, but increase travel time up to like 286%. For this multi-objective equal routing, we could save BEV energy consumption up to 27%, and then ICEV BEV fuel consumption up to 10% when we assign both ICEV BEV HEV in the same network. And multi-objective equal routing also saves the travel time up to 70% at 100% market penetration during heavy congested traffic conditions. So the final was is this result indicate that developing multi-objective equal routing algorithm can reduce ICEV, BEV, HEV energy fuel consumption with minimum impact on time. The future work, and we need to investigate the optimum coefficient for the multi-objective equal routing model that reduce fuel energy consumption and travel time including different combination of various vehicle types, equal routing market penetration, and different congestion levels and different network configurations. That means if you use exactly the same algorithm in New York City, then result can be different. This is the end of the presentation.
Thank you very much for the very interesting topic and presentation. Any questions? Any questions from audience? Okay, I'll ask the first question. Is it feasible to implement it in the real world?
Yes, it is possible. Let's say, let's assume if we are Google or Apple, then we can get all the traffic information from Google Map users and then Apple Map users. In that case, since we know all the travel time information, and then regarding the fuel consumption and emission information, we can estimate using our model. In that case, we can assign the people with a more energy efficient route. So the NCCF is not easy.
Great. That would be so interesting to have such an algorithm working in the real world. Any questions, audience? Do we have some in the chat? No. Okay. Thank you very much, Dr. Ann.
Thank you.
Our webinar is 1 hour slot, and we don't want to change the timing.